Okay, so in this problem we're asked to explore a bit a concept known as center of percussion. Center of percussion actually is a concept that for years has been rumored to be involved in the design of baseball bats. I maybe have some doubts about the legitimacy of that statement, but I'll leave it to you to see whether or not it turns out to be true. In this particular problem, though, what we're asked to do, or we're told, is that the location of center of percussion for a rigid body is given by h is equal to I naught divided by md, where h is the distance between the support point O to point P, the center of percussion, and d is the distance from the support point O to the center of mass G, and I naught is the mass moment of inertia of the body about the support point O. In this example, we're asked to explore the free vibrations of the baseball bat suspended from the support point O and to determine the location of the bat's center of percussion. To do this, we're asked to start by drawing a free body diagram of the bat, then to develop the equation of motion of the bat in terms of the angle theta using small theta approximations. We're asked to linearize the system and figure out the natural frequency of the response of the bat in terms of the parameters in the problem. Finally, we're asked to determine the relationship between the distance h to the center of percussion and the natural frequencies of free oscillation. And finally, we're asked to talk about how we could set up a simple experiment to determine the center of percussion of the bat. So let us start by drawing a free body diagram of the system, and I'll probably draw a bad sketch here, but here's our baseball bat. And we know in this case that the only forces acting on this bat, if it's suspended by the support point O, will be the reactions at O, which are given by OX and OY. And the weight, which of course will be located a distance, in this case d, along the bat. Likewise, I know that in terms of kinematics, we'll simply have rotation about point O given by I about O theta double dot. So if I want to find the equation of motion for the system, all I really need to do is sum moments about point O and do so in a counterclockwise positive sense, and I'll get that that's equal to I about O times theta double dot. And if I write this down here, the only force that's going to contribute a moment is going to be the weight, so I'll have minus mg. And if I note that this little interior angle here is theta, the part of the weight that will contribute a moment is mg times the sine of the angle theta. And I need to multiply that by the moment arm length, which in this case will be distance d, and that will equal I about O times theta double dot. Now I can get the full equation of motion for the system simply by rewriting this, and if I do so, I'll simply get that I about O times theta double dot plus mg times d times the sine of the angle theta will equal 0. Now this is a nonlinear differential equation of motion, something that most of you wouldn't study until graduate school should you choose to move on with that. And so what we typically do is we assume small angles, which allows us to replace the sine theta term here with theta. And so under the small angle approximation, what we can do is say this is approximately the equation of motion given by I naught theta double dot plus mgd times theta is equal to 0. And that would be the equation of motion we would want to use for analytical purposes. Now given that, we can actually find the natural frequency of the system simply divided through by I naught, and so we'd get the natural frequency would be the square root of mgd divided by I naught. Now if we want to express this in terms of the center of percussion distance h, we could note that h is equal to I naught over md, which means this is simply equal to the square root of g divided by the center of percussion length h. Now, that's really what this problem is looking to find. Of course, a more accurate thing is, well, how could you conduct an experiment? The way I would conduct an experiment would simply be to say, well, if we know that relationship in the prior line exists, the equivalent statement is that omega n squared is equal to g over h, which of course means that h is simply equal to g divided by omega n squared. And so if we were to simply suspend a bat by its free end, set it into free oscillation, and to measure its period, we could then compute the natural frequency from which we could get the center of percussion for the system. That's what I would do, and I bet you can do the same. I wish you the best of luck as you work through this problem.